The Think Well videos pretty much just look at work in terms of springs. And again, the basic idea of work, to calculate work, it's force times distance. So a very basic problem would be if you lift a 10-pound box and you lift it 3 feet, 10 pounds times 3 feet would be 30 foot-pounds. Do you need your calculator for that one? So 30 foot-pounds of work. Now, the problem we're going to run into with the springs and what we'll talk about here today, in some cases, we do not have a constant force. Okay. The 10-pound box, well, I guess tremendously theoretically, it's not a constant 10 pounds in that 3 foot of movement. But it's so very, very, very close to 10 pounds the entire way. It all depends on the gravitational force of the Earth, and it's going to be just slightly, ever so slightly different as you move away from it. Now, for practical purposes, you and I being on the surface of the Earth, it's not going to change. But when we start talking about space, trying to launch a satellite into orbit of the Earth, well, the work done on it's going to take a lot more, there's going to be a lot more force applied at the surface of the Earth than it is 20 miles above the surface of the Earth. The force of gravity reduces at the farther away you go. So that's why we have to look at force in those terms. And what we find with force of launching a rocket or something like that, we can say the force of gravity on an object propelled, launched, whatever you want to call it, above the Earth is inversely proportional. Now we'll talk about what that means. Surely you've seen that before, but probably have forgotten. Inversely proportional, not proportionality, but proportional, there we go, to the distance from the center of the Earth. I guess technically I should be capitalizing Earth. We'll get that on there. Okay. Get correct English on here. Now, this is how the descriptions in problems 11 and 13, okay, or for numbers 11 and 13, this is how we're going to find the force function. And it also says neglecting air resistance and the weight of the propellant, okay, not the weight of the object we're putting up there, but the weight of the rocket to launch it. There's a lot more details that go into these than we can handle at this moment, but we'll reduce it down to just kind of the real basics. So the force of gravity is inversely proportional to the, actually it shouldn't be just to the distance, but to the square of the distance. Square of the distance, not just the distance. Okay, so we let force be F. Now, inversely proportional, any proportion, you're going to have a proportionality constant multiplied by whatever we're dealing with. That's kind of like your paycheck is, thank goodness, directly proportional to the hours that you work. Well, it's not just your paycheck equals the number of hours you work. That would be sad. That would basically mean you're making $1 an hour. But that proportionality constant is your hourly rate. So your salary would be $10 times time, or maybe $5. Some of you aren't worth as much as others. But no, whatever your hourly rate is, that's what we call your proportionality constant. We're going to have that anytime we deal with a proportion, whether it's direct proportion or, in this case, inverse proportion. We use K for that proportionality constant. So now in this case, we're inversely proportional, so that means we're going to divide by that value. And we're going to divide by the square of the distance, and we'll call x the distance. So the force of gravity on this object will be represented by k divided by x squared. Okay. Now this is from the center of the Earth. One important piece of information here: what is the radius of the Earth? Because this isn't from the surface of the Earth, this is from the center. So the radius of the Earth we will be using 4,000 miles. Now, of course, that depends on exactly where you're at on the surface of the Earth, but this is going to be close enough for our calculations, no matter where you're at. So, when you think of from one sea level to the top of a mountain, what's the difference there? Well, Denver is called the Mile High City. Its elevation is approximately 5,280 feet. So it's 1 mile above sea level. So from sea level up to the top of a mountain, some of the highest mountains are maybe 12, 13, 14,000 feet, 2 miles maximum. There's not a lot of difference between sea level and top of a mountain when we're talking the radius of the Earth. We'll go ahead and assume the radius of the Earth is the same at all of our points. Okay. Again, not necessarily exactly what we would need to worry about, but for now, that's all we're going to deal with. We're also neglecting air resistance and a couple other things. But for the force, okay, the force varies, force of gravity will vary as that rocket travels above the Earth. And that's what we'll be using for the force. Distance that it travels, that's also calculating the work. And he explains it on the Think Well videos in terms of springs. Force, Hooke's law for springs is the force is directly proportional to the distance the spring is stretched. So for springs, it's F equals K times X. About as easy as you can get. But a little bit different. Inversely proportional to the square of the distance. Well, still F equals K, but then divided by X squared rather than times X. Okay? So that'll be used in 11 and 13. And our next example, we'll go through a lot more of it, but our next example will be pumping water out of a tank, how much work it takes to do that. Okay, so on the worksheet, number 15 and beyond, all of these will deal with our force of gravity, well, that represented by weight. So we've got to be able to figure out how we can represent the weight of a certain object or a certain portion of this object and find the work from there. Well, let's go ahead and look at a particular problem. Number 18, we'll go ahead and run through number 18 on the worksheet. Okay, lots of details here on our problem. Refer to the picture as well. Probably looks a little bit better than mine. But, circular tank, 4 meters high, radius of 2 meters, and it's set 10 meters above a stream. And we are to calculate the work that it takes to fill the tank half full. Okay. If there's some hole in the bottom that we're pumping the water in through. Well, with work being force times distance, well, we have a couple of problems here. What's the distance that the water is pumped?
10?
No, it's more because it's going to reach up to...
So it'll be 10 plus...
It depends. If we take a slice here out of the bottom, or out of the tank, it's going to depend how far we've pumped it, depending on where the water ends up. The water at the very bottom of the tank will have been pumped 10 meters, but the water at the top of our situation, half full, will be 12 meters. So we don't have just a set distance that we're pumping this water. It's going to vary. It's going to depend on where the slice is. So how can we represent this slice?
dy?
Not dy.
Just y?
Okay, we're moving it from here up to here. That's going to be a value of y. Okay, so the distance we can represent as just y. Okay. Now what about the force?
It's going to be decreased because it goes up, right? The force from gravity.
This is one of those, we're not going near far enough to worry about the change in force.
So it'll be the change in y?
Well, the force in this case, we need to think about the weight.
The weight of the water is increasing.
The weight of the slice here. Well, when we slice this, what object or what are we really looking at?
A disc.
A disc, a cylinder, very short cylinder. So we can kind of think of it like that. Okay. And weight, well, we kind of have to back up and say, okay, how do we calculate the weight of this disc? Weight is, well, it depends on what type of liquid we're pumping, the density, times, well, how much of it there is. So the weight of it will be density times volume. Now the density, we're going to be talking about water. I think all of our problems are water unless, yeah, H2O.
It's 1 gram per milliliter, right? Pretty sure.
Now, some of the problems might talk about, I think one or two of them talks about a gasoline, and it has a different, it'll give you the density for it. But the density for water is, well, in the English version, it's 62.4 pounds per cubic foot,
It's so horrible.
or the metric version, it's
1 gram per milliliter.
yeah 9,800 newtons per cubic meter, or whatever other conversion, yeah. But
The volume will be.
That's not weight.
so density, depending on which system you're working on, you might be using 62.4, but in this case we'll be using 9,800 for that part of it. Now that's not going to change. Water, density of water stays the same in our situations. There might be some rare cases in your upper level, either chemistry or physics or something like that. It might hit a situation where it changes, but for us it's not going to change. Well, let's take a look at the volume of this slice. Now this is a circular cylinder basically, and the circular cylinder, it's going to be pi r squared h. And we also need to look at all of the different possible slices. Is anything changing? Well,
I mean,
Changing why?
yeah.
okay, we can represent the height of this as what you guys were saying, the change in y, delta y, or will turn into dy when we integrate. What about the radius? What's the radius of this slice?
Just why?
2 meters.
Oh,
Okay, yeah, no matter what, the tank is right circular cylinder, so the radius of it is not changing no matter where we slice it. Even if we went clear up here, it would still be 2 meters for the radius. So in this case, the volume is pi times our 2 meter radius, square that, and then times
dy.
dy or delta y. So integrating, let's see. I think we might have enough room if I write small enough. Integrate from where to where?
From 0 to 10? Oh, it's from.
Or to y? Is it 0 to y?
What slices are we dealing with? What's the lowest our
10.
10.
slice? Okay. Lowest would be our 10. Where would be the highest?
12.
Okay, so we're going to be integrating from
Oh,
10 to 12.
that makes sense.
Okay.
Can you integrate from
It
0 to 2?
should sound worse than that, but no, it's
Can you integrate from 0 to 2?
integrating from 0 to 2, we'd have to make some other adjustments.
Okay.
But the easiest thing to think about, integrate from 10 to 12, because again, that's where we take our little slice of our situation. Okay. And then we have force. What did we say our force was? Well, our force is the weight, density times volume. So 9,800 newtons per cubic meter times volume,
Which is 4 pi.
which was our, pi times r squared times h. So 2 squared, r squared times pi. And we'll save the dy for the end of the integral, but that would technically be part of the force or the weight. Times the distance. And what did we say the distance was? Okay. And then the dy.
That's actually pretty cool.
And yeah, the integral will actually be very simple to work out, but getting there, there's a lot to it.
Yeah.
But it's basically force or figuring out what the weight is of a local estimate, slice, whatever you want to call that, times your distance.
When you put those tanks up in the really high, you use the equation where is equals times 4. So.
Yep. To calculate the amount of work it takes to pump that water up to that tank. So,
That'd be like a water tower or something?
yeah, water tower. Now, water towers don't quite look like that, but it's the same idea. The calculation would be a lot uglier. Water towers, most of those are what, spheres?
Because some of them, like the ones we have, go.
Yeah,
No, they're
they're different shapes, but a lot of them are
Like a cup
spheres.
looking
So.
thing? Cup looking
Yeah.
thing?
It's even worse than this.
So that would get real ugly, but setting it up is one thing. Calculating it, once you get it
Should be the
set
same
up,
method?
calculating
Should be the
it's
same
not too
method?
bad. But any of the work problems, what's the work done in pumping water so far into a tank, or maybe in problem 17, a tank is buried under the ground and it's pumping it out. That's some of your gas stations when you fill up with gas. Their tanks are under the ground and it's pumping it up into your gas tank. So same situation, but you got to take into account slightly different details of it. So, any questions on those?
So what about using differential equations for that?
No differential equations yet. Not for these guys. But okay.